To finish off, we have a worked example of a bending member capacity check, and it's the same example that we visited for the serviceability worked example. So it's floor joists, they're MGP 10, and we're looking at a combination of permanent action and imposed action due to a crowd. So the first thing to do is to calculate the actions on the member. And these are strength limit state actions, so we're using strength limit state factors to evaluate the strength limit state loads and then use those to evaluate the strength limit state bending moment. And it is going to be a function of the types of loads that are in the load combinations. So we can evaluate what the moment is that we have to resist. That is the strength limit state moment, M star. The rest of the worked example looks at evaluating the design capacity of this particular member. And because this is an office with a large number of parallel joists, these joists are all secondary. So we can look up the capacity factor for sawn timber, MGP 10 grade, and used in a secondary roll. And that gives us a capacity factor of 0.9. Then there are the K factors, and these are going to be different for each of the load combinations. So under permanent action alone, it's 0.57. Under the action of permanent loads and imposed loads together, it's going to be the duration of the imposed load that dictates it. So for imposed loads like furniture that are going to be acting for a very long period of time, our K1 factor is 0.57, but for crowds, which are only going to be acting for days at a time, it's the days K1 factor, which is 0.94. It's seasoned timber used indoors appropriately with K4 equals 1. Adelaide is not in the high temperature zone, so K6 is 1. And then we can evaluate the strength sharing factor. In this case, each member is not nailed to other members alongside of it, but it's used in a discrete system. So NCOM is 1, and we're going to use NMEM as 3. So bearing in mind the length of the member and the spacing of the members, we can calculate a K9 value. And notice that it is bigger than 1. It's 1.13. So it's saying we get an increase in capacity due to the strength sharing factor. And finally, the stability factor. So here we look up a material constant, our row B from a table, table 3.1, and we evaluate the slenderness for the case where we have a gravity load that's putting the top into compression and we've got restraint across the top. We're told the distance between the floor fasteners, and we use that as our LAY in order to evaluate our slenderness. We find that the slenderness is 8. And so our row B times our slenderness gives us a value less than 10. It tells us that this member is used in a stocky way, and our K12 value is going to be 1. So our capacity check for bending is going to involve putting all of those elements together along with our Z value. It's used in major axis bending, so our depth is the 140 millimetres and our breadth is the 45 millimetres. And so calculating all of that, we can find a design capacity and compare that against the design loads that we had previously evaluated. So bending capacity. We also have to check shear capacity and bearing capacity, but that's not covered in this module, and the serviceability check that we have done in a previous module. Bending members have to be checked for strength limit state, and in most cases they also have to be checked for serviceability limit state. The capacity factor ensures consistent reliability across all members and all types of members. The K factors, the modification factors, allow for design conditions and the service environment in which the beam is going to be used. And potential for buckling is considered by using the K12 factor. Once all of these are assembled, we have anticipated all possible failure modes of our bending member and ensured that it will resist the strength limit state loads.